Right, okay. Shall we start? Can you hear me? Another one?
Yes.
Okay. Right, so last week we have stopped in horizontal alignment part. Right, we were discussing about the horizontal alignment. So when we consider about the horizontal, so I will continue from that point today, right? So when we consider about the horizontal alignment of a road, so it will consist different forces, right? Like this. So if a vehicle is moving like this in a horizontal curve, right, there will be a centrifugal force acting on the vehicle outwards of the center, right, away from the center. So due to that force, this vehicle will move away from the road or move away from the curve, right? Then to counter effect that one, we have the friction force and the force due to the inclination of the road. That we have the friction force and the force due to the inclination of the road, right? So the balance of these two forces will keep the vehicle in the road, right? Then first we have to consider the basic curve equation, right? So you have seen this in a horizontal curve, the road is not flat. The road is not flat, it's something inclined, right? You have seen this one, right? So mostly in the racing tracks you can see this one very clearly, but in the normal roads also we have this inclination. So this inclination we call it as the super elevation. We'll discuss that later, right? Then the basic curve equation, right? uh, we have a vehicle here. So if we consider the forces acting on this vehicle, right, we have the reactions coming from the road Ra and Rb, and we have the frictional forces Fa and Fb, right, and we have the weight W, right, and the P, centrifugal force, right? Then if we take the component, so this is W. For this side, the component is V sine theta, and for this side, we have the component V cos theta. And from this force P, in this direction we have P cos theta, and in this direction we have P sine theta. So that comes like this. So here the angle is theta, this angle is theta, then this is 90 minus theta, this angle, and this angle also 90 minus theta, then this angle will be theta. This is theta, and this is 90 minus theta, and this angle again, this is theta, right? Right. Then we'll go to the we'll develop the curve equation, right? The centrifugal force P is equal to WV squared over 12.96 GR. So this is something like in A levels we have F is equals, we have the equation F equals ma. F equals ma. So here the centrifugal force is P, and the mass is W divided by the weight divided by the gravitational acceleration W over G. Then acceleration is V squared over R, right? V squared divided by R. So WV squared is okay, GR is okay. Then what is this 12.96? So that is from the sign convention, right? So we apply V in kilometers per hour, then we apply R in meters, then G is ms minus 2, W is in kilograms. So likewise we have different signs for this one. So when we convert that signs, right, this 12.96 will come, right? Then considering the equilibrium of the forces, so I will take the equilibrium in this direction. P cos theta is equal to W sin theta plus Fa and Fb. P cos theta is equal to W sin theta plus Fa plus Fb. Then P cos theta equal W sin theta. Uh, the friction. So in A levels we know that frictional force is equal to mu into R. Mu is the uh, coefficient of friction and R is the normal reaction. So the normal reaction is W sin theta. So this is normal reaction. These two, right? RA plus RB. RA plus RB is equal to W cos theta plus P sin theta. So this is equal to F is the friction coefficient times W cos theta plus P sin theta. Then if we divide this one by W cos theta, then this will be P divided by W, and this will be W and W will be cancelled out, and this will be tan theta plus F minus 1 minus F cos theta. So, because there is a P here, so we can divide this one by W cos theta, then take this P to this side and subject, then we can come up with the equation P over W is equal to tan theta plus F divided by 1 minus F tan theta. Right? Then the tan theta is the tan value of the super elevation or the inclination. We call it as E. Right? And POW is equal to F. So you can substitute P over W. This is P. Right? Then P over W is V squared over 12.96 dr equals E plus F divided by 1 minus EF. Right? Then here we have a small assumption. Here F is the coefficient of friction. So that is something like 0.0035 or 0.035. Right, F is 0.035, then E is also a percentage, something like 2% or 3% or something like, then that is 0.02 or something. Then E into F, so that is almost equal to 0. That is a very small value. Therefore, we can take that EF is equal to 0 and G is 9.81. Then we can, from this equation, we can calculate the value of R, that is V squared over 127 E plus F. So this is called the basic curve equation. Right, so is it clear? Harida, තේරෙන්නත අහන්න. හරිනේ, right, then එහෙනම් ටක් ලියමු. So you can draw this one quickly. So today we have to work somewhat quickly, right? Because we have limited time, so we have to do some more work. But therefore, so please be quick, right? Right. Then the second slide. Right. Then last slide. Right. Now this is the equation, right? R is equal to V squared to 127 E plus safe. So if we know the value of the E or the super elevation, and V is the design speed, and if we know the friction coefficient, then we can calculate the required radius for that curve, right? Or the other way around, if we have the radius value, then we can calculate the required super elevation for that row. So likewise, we can calculate in different scenarios, right? So we'll see example. Right, before moving to the example, there are some maximum radius uh, required spirals. That means if the speed is less than 60, no need to have a spiral curve. If the speed is 70 kilometers per hour, then we need to have a spiral of 220 meters. Right. So likewise, depending on the operating speed, there are different maximum spiral length, spiral radius, and also a minimum spiral length. Right. So those are several values. Right. So this is the design process of uh, designing a horizontal curve like this, right? So we select the curve radius for the design criteria. Then we check that this RC is less than minimum radius requiring a spiral. Right? We check this one whether we need the spiral curve. If it is no, then we can go with the full circular curve. Then we select LE and SRO. So those LE is the super elevation development length and SRO is the super elevation runoff length. So we'll discuss them later, right? So we have to select those two values. Then again we check whether we need the spiral. If it is yes, then we go to a spiral circle spiral. If it is no, we are going with the full circular curve, right? So you can't understand this part now, right? So after we finish the super elevation part, I will come again for this chart. Then you will be understand, right? Then minimum curve radius. So the curve radius will be minimum when the denominator is maximum, right? V is the constant, that is a design speed, that is constant. So when the denominator is maximum, then the radius will be minimum, right? So we can maximize the denominator, we can increase the super elevation. So if we increase the super elevation, it will reduce the curve radius. Or if we increase the friction coefficient, again the radius, we can reduce the radius, right? Exercise: an horizontal existing horizontal curve with super elevation 3 degrees, then E is 3, has a radius of 100 meters. Here E is 3, not 3, tan 3. Then radius is 100 meters. F is 0.15. Then they are asking the value of V. Right, then here if the curve is improved to a design speed of 70 kilometers per hour, what is the minimum radius of the curvature is required? Then here they have given the V value and they are asking the R value. Right, so the new thing is super elevation is 3 degrees, means we have to substitute E equals tan 3. Right, so I will give you 2 minutes. You can write down this question. Then you can try for only 5 minutes, right? I will give 5 minutes. Right, then we'll discuss again. Right, we'll see the answer. Right, so the data given now, R is 100 meters, theta is 3 degrees, F is 0.15, then E is equal to tan theta, that means tan 3. Then the equation for the radius is V squared over 127 D plus F. So we substitute. R is 100 meters, V squared we don't know, 127, tan is tan 3, F is 0.15. Then V squared is 2570.58. You can use the calculator. Right, then V is equal to 50.7 kilometers per hour. Then for the second case, they have given the velocity as 70 kilometers per hour. Then minimum radius is V squared over 127 E max plus F max. So now the speed is 70 and E is tan 3 and F is 0.15. So you can calculate the radius. So here you can see for the radius of 100 meters, we can go only up to 50.7 kilometers per hour. But here, for the velocity of 70 kilometers per hour, we need a radius of 190.61 meters. That means we have to increase the radius, then we can increase the design speed. Right, so that is the scenario. Right, we can write down the answer. So if we have any questions, we can ask any time, right? Right. Next, the maximum super elevation. At the maximum super elevation, we can control it by three factors. One is terrain, right? Whether the terrain is flat rolling or mountainous. So we can control the maximum super elevation and type of the area, whether it is a rural area or a urban area. We have minimum or maximum super elevation values. So that is depending on the terrain type and the type of the area, and frequency of slow moving vehicles also might be influenced by high super elevation rate. So as I mentioned, when the super elevation means that inclination, right? So when that inclination is increased, it will be very easy for the vehicles which are moving very fast. But if the inclination is very high, so it will be very difficult to drive slowly in that road. නිකන් හිතන්නකෝ ගොඩක් ඇද පිට වෙන මෙහෙම තියෙන පාරක වේගෙන් යනකොට ප්‍රශ්නයක් නැහැ, දැනෙන්නේ නැහැ, ඔක යනවා. හරි හිමින් යන්න බෑ. ඒක කියන්නේ දැන් අපි හිතුවොත් පාරක් මොකක් හරි ලොකු ට්‍රැෆික් එකේම සෙට් වෙන පාරක නම් right පාර මෙහෙම ඇද වෙලා තිබුණොත් එහෙම යන්න අමාරුයි. But therefore we have some maximum value for the super elevation also, right? So if it is a flat terrain, whether it is open area or build up area, we can go with the maximum super elevation of 6%, right? If it is a open rolling terrain, for a open area we can go for 8%, for a build up area we can go for 6%. Then for a mountainous terrain, for an open area we can go for 10%, and for a build up area we can go for 6%, right? So that is the maximum super elevation. Then if it is an urban area, for all speeds the maximum super elevation is 5%, right? If it is a high speed rural area where the speed is greater than 90, we can go for 6%. Likewise, this maximum super elevation will depend on the terrain type and the road type, right? Then the minimum side friction factor, the maximum side friction factor, so that is depending on the design speed and the road condition, whether it is a bituminous or a gravel surface. And these are some super elevation values given in the design guide. The minimum curve radius according to the super elevation and the speed. Right, here we have the speed, here we have the super elevation and the minimum radius. So we are using this one like this. So we calculate the required radius from that equation, right? Then we get some value. But then we have to check that value with this minimum curve radius. If our value is less than the minimum curve radius is 90, and if our value is 75, so we can't go with 75. We have to go with 90. Right? So if so that is the scenario, right? So this is the minimum, 90 is the minimum. And if our calculated radius is 100 meters, and here the minimum is 90, then we have to go with the 100-meter range. But if it is greater than the minimum, we have to use the calculated one. If the calculated value is less than the minimum, then we have to use the minimum one. Right? So that is the scenario. Right. Then the super elevation. Right. Minimum super elevation is required to cater drainage. So I have explained this one, right? In a normal road, we have a small super elevation like this. I explained this one previously. This is only for the drainage purposes. Right? We call this as this super elevation as minus 2.5%. Here also this is minus 2.5%. Right? That is the minimum super elevation. We call this one as the normal crossflow. Right? We call this one as the normal crossflow. Right? This value changes according to the design guidelines, and in normal Sri Lanka, we consider this as minus 2.5%. Right. Also, we call it as the adverse crossfall also. The adverse crossfall is minus 2.5%. Then the side friction is 0.06 for open areas and 0.07 for build-up areas. Right, so these are minimum. Right, then we'll go to the super elevation part. Right, this is somewhat interesting part, right? The super elevation to be adopted is chosen primarily on the basis of safety, but other factors are comfort and appearance. So we are using the super elevation basically to improve the safety, but also we are using this one to improve the comfort and the appearance also. Right. So this is the maximum super elevation that we have discussed in the previous slide. Then the minimum super elevation is the normal cost minus 2.5%. Right. Then we have to discuss about the horizontal curves. Right. Again, we have one exercise. This is also from the previous equation, the equation for the radius. Right, the radius of the horizontal curve is 100 meters. Then this is r. R is 100 meters. Then the design speed v. V is 50 kilometers per hour. Then the design coefficient of lateral friction 0.15. This is f. Calculate the super elevation. That means they are asking to calculate the value of E. And second one, calculate the coefficient of friction. Right, that means they are asking the value of F. If no super elevation means E is equal to 0. Right, first scenario they are asking the value of E. Second one they are asking the value of F, uh, where the E is equal to 0. Right, so I will give you another 5 minutes so you can quickly try this exercise. Right. Shall we discuss the answer? Okay. The R is 100 meters. Yeah. R is 100 meters. V is 50 kilometers per hour. F is 0.15. So they are asking the value of E. So I will subject E plus F here. Right. Previously the equation was R is equal to V squared over 127 E plus F. Now I subjected E plus F. Then E plus F is equal to V squared over 127 R. Right. Then F is 0.15. V is 50 kilometers per hour divided by 127. R is 100. Then the super elevation is 0.047. That means 4.7%. Right, or we can say it as 1 in 21.34. Right. Uh, yeah. That is normally that is 4.7 divided by 100. So that value is 21.34. Right. 4.100 divided by 4.7. Right. Second case, they are asking us to calculate the f value if e is equal to 0. Right. E plus f is, so here there is no any f value here. This is not here. Right. E is 0, then 0 plus f is equal to 50 squared or 127 into r. F is equal to 0.197. Right. So you can uh, take the answer if you need. Right. මොනවද ප්‍රශ්න තියෙනවද? තියෙනවා අහන්න. right? Then we'll go for the super elevation, right? It's something like this. So this red color one is the straight road or the tangent. This blue color one is the horizontal curve. Right? This image is taken from the sky. මේ අහසින් අරන් තියෙන. ඒතර මේකේ කෙලින් කැල මේ මෙතන වලට පේනවා මෙතන වංගුවක් තියෙනවා. Right? In this red color section or the straight section, road is something like this. We have the normal cross pole. Here the super elevation is n is minus 2.5. Right here you can see this is a curved section. In the curved section, the slope is in the same direction. In this case, slope is in either directions from the middle, but here the slope is in the same direction. So that is the scenario of super elevation. Right, we'll see. Right. Attainment of super elevation. Change of super elevation from normal cross pole to full super elevation. The length is called super elevation development length, LE. Must be done gradually over a distance without appreciable reduction in speed or safety and with comfort. Change in pavement slope should be consistent over a distance. But that means, so we have to take the road from this condition to this condition. So we can't do it directly. මෙහෙම තියෙන පාර එකපාරම මේ පැත්තට උස්සන්න බෑ. But we have to gradually rotate this pavement in this direction. හරි මීර මේක උඩට හරවන්න ඕන මේ පැත්තට. ඒක තමයි මෙහෙම එකක් හැදෙන්නේ. Then finally it will be like this. Right, initially it was like this. Right, therefore we have to do it gradually so that over a distance. So that distance is called the super elevation development length, LE. Right, so there are several methods to attain the super elevation. We can rotate the pavement about the center line, or we can rotate the pavement about the inner edge, or we can rotate about the outside edge. Right, we'll see. Right, the total length required to develop full super elevation is called the overall length of super elevation development, LE, and it will consist of two components. Tangent runout length, we call it as TRO, and super elevation runoff length, that is SRO. Right, that is SRO. So now this is something like this. Right, so listen very carefully at this point. Right, මේක හරියටම අහගන්න. Right, like this. Now this part, this red color part, and here this part. So these two parts are the tangent. මේ තියෙන tangent. Right, here n means we have the normal cross pole, minus 2.5 to minus 2.5. Right, so this bottom figure, this is a cross section, a side view. So in the straight section, we have the normal cross pole. Right, this is outage. ඔය ඇඳලා තියෙන outage එක කියන එළිය, this line. I will use another color. Right, this line. This line is here. Right, and the center line. This is the center line. Made in matter. The elevation of the center is higher than the edges. Edge එකට වඩා කෙළවර මේ මැද උසයි පාර. Right, then this is the other edge, අනිත් edge. So that is also in this level. In the straight section. පාර කෙලින් තියෙන හරිය මැද උසයි දෙපැත්තේ edge දෙකම එකම level එකේ ඊට වඩා පල්ලෙහායින් තියෙනවා. Right, then from this point onwards, it will start the super elevation. Then this pavement will rotate like this in this direction. මේ pavement එක මේ පැත්තට rotate කරනවා. And take it to zero level. කළා මේක ගේනවා 0% වලට. -2.5 තිබ්බෙකනා දැන් ගේනවා 0% වලට. Right, that is the first case. So if we draw it in this diagram, the center line is remain same, center line, and this green color edge, that is also remain same. Green color edge එකත් ඒ විදිහටම තියෙනවා here. Right, then this blue color edge, so the elevation of the blue color edge is increasing with the time, with the distance, right? ඒක පොඩ පොඩ වැඩි වෙන්න ගන්න. Right, here you can see this is the green color edge and come to this point. Right, then this distance, we call this distance as the tangent runoff length, TRO. Right, then next step, we will rotate this pavement also. Right, තව ටිකක් ඔන්නෝක කරගනවා and take it here, then this will be a straight line. මේක කරකලා ගේනවා I. So this was -2.5 and this will be also, this will be +2.5 over 2.5 එකක් ගේනවා. Right, I can explain it like this also. Like this. Initially we have -2.5 and -2.5. Then we rotate this pavement, this blue color one, then take it to the flat level to this point. Then again we rotate this one and take it to this point, align with this pavement. Again we rotate this one, this side, and take it to this level like this. Right? So I will rotate this one, take to flat level, again rotate, take to this level. Then again when we are rotating this one in this side, and we rotate this one in this side. They're not ready. අර එහා පැත්තේ edge එක මේව කරගලා මැද්දට ගේනවා. ඊට පස්සේ තව ටිකක් කරගලා අරකට ලයින් වෙන විදිහට කියනවා මෙන්න මේ විදිහට. right, ඊට පස්සේ කරගෙනකොට දෙන්නත් එක්කම කරගවන්න ඕනේ. පැහැදිලිද ඔය කතාව? මොකද තමයි පොඩ අමාරු එකට දෙන්න පැහැදිලිද කතාව? හරිද? මොන හරි තියෙනවා නම් අහන්න කතා කරන්න මේ. අයියෝ. හරිද? Right. Then when you are reversing that turn also same, right? So if you have 5%, rotate and take to 2.5, then rotate this side only, take to 0, then again -2.5. Right, then this length, the length that is required to take this one from the normal cross fold to the flat elevation, flat level, flat cross fold, that is called the tangent runout length. the length of roadway required to accomplish the change in crossflow from a normal crown section to a flat crossflow like this. Right? Then that is tangent runoff length. Then super elevation runoff length, this one, the length of the roadway needed to accomplish a change in crossflow from flat crossflow to a fully super elevated crossflow. Flat එකෙන් ඉඳලා full super elevation එකට යන්න ඕන distance එක අපි කියනවා SRO කියලා. Right, and there is a equation for SRO, that is LE minus LE times N over N plus E. That is super elevation runoff length. Right. So now what you have to do is you have to draw this picture. Draw this picture and this picture. ඔන්න ඔය දෙක ඇඳ ගන්න ඕන පැහැදිලිව. නැත්නම් තේරෙන්නේ නැහැ වැඩි. So meanwhile you can take a break, right? And after the break we'll start again. So I will keep this one so you can write down, right? Meanwhile you can do. Right. Shall we start again? Okay. So I think you have drawn this one, right? Okay. Then this is tangent runout length and the super elevation runoff length. Right. So the equation for the super elevation runoff length. So you can write down this one also. Right. SRO is equal to LE minus LE times N over N plus E. Right. This is the equation for the super elevation runoff length. And the tangent runout length, so that is LE minus SRO. So we have to calculate the SRO value. Then there are several methods to calculate LE. So we'll go for that one later. Right. For the moment, you can write down the equation for TRO, tangent runoff length, LE minus SRO. Then you can write the equation for super elevation runoff length, LE minus LE times N over N plus E. Right. Then there are two methods to calculate the super elevation development length. Right. First method is relative gradient method. Uh, Second one is rate of payment rotation method. Right. So in these two methods, we are calculating two criteria actually, right? So in the relative gradient method, so that will focus on the appearance criteria, and for in the rate of payment rotation method, so it will consider the comfort criteria. So, right? So what you have to do is, so we are doing the calculation from both of these methods and get the highest value. Then it will satisfy appearance and also the comfort. Right. So we'll see. So this is the relative gradient method. So the super elevation development length L is equal to W times E plus N divided by GR. Here W is the lane width, N is the super elevation, N is the normal crossfall, GR is the relative gradient. Right, we have different relative gradient values uh, defined for different speeds and different roads with different lanes. Right. So we can select the appropriate value from this one for different speeds and for different lanes, and you can directly substitute here and you can get the super elevation development length. Right. So take 1 minute and write down this equation and this notation. right? Then the second equation, the payment rotation method, right? The rate of payment rotation method. So in the rate of payment rotation method, we are using a beta value, right? So here LE is E plus n divided by E plus n times V divided by 3.6 beta, right? And here the others are all the others terms are same, and the beta is the rate of payment rotation. If the design speed is less than 80 kilometers per hour, beta value is 0.035, and if the design speed is greater than 80 kilometers per hour, beta value is 0.025. So when you are substituting for this one, so there is a small thing here. In this case, the relative gradient is a percentage value. This is a percentage value, right? E and N also are percentage values. So when you are substituting for this equation, E and N, so N is 2.5, E is something 5 or something, right? You can substitute as a percentage value. So you can directly substitute 2.5 here, and GR you can substitute from this table. But in this case, here beta is not a percentage. Therefore, when you are substituting for this equation, you are substitute as a decimal case. Right. Then we'll go for example later. Right. Then for a single circular road, 2/3 of the length of development is provided prior to the tangent point, and 1/3 is provided within the curve. So this super elevation development length is that the length where the pavement is rotating, right? So we calculate this length, and we have to keep 2/3 of this length in the tangent. Right? That means like this, we have a straight section and curve section. This is the tangent point, right? So if we have the super elevation development length, so if this is the super elevation development length, so we are going to start the pavement rotation here and make it to the full super elevation level here, right? Then we have to keep 2/3 of this length along in the tangent part, or before the
Not visible.
what was it? පේනවද කරන එක?
Yes, පේනවා.
Yes, right now.
හරි. එතකොට මේ අපි දැන් super elevation development length එක ගත්තට පස්සේ මේකේ straight section එකයි curve section එකයි තියෙනවා. ඒතර මේ length එක තුනකට බෙදලා දෙකක් තියන්න ඕන මේ straight section එකේ. කියන්නේ අපි මෙතන ඉඳලා තමයි වැඩේ පටන් ගන්න. කියන්නේ අපි super elevation development length එක හොයාගන්නවා LE. LE හොයාගෙන අපි මේක බෙදනවා තුනකට. We divide this super elevation development into 3 parts. Right, then we start from here, keep 2/3 to this side. අපි මෙන්න මේකේ මෙන්න මෙතන මේ tangent point එකට ඇවිල්ලා tangent point එකකින් ඉඳලා මෙන්න මේකේ මේ දුරෙන් දෙකක්, මුළු දුරෙන් තුනෙන් දෙකක් තියලා මෙන්න මේ point එක මාක් කරගන්න. මෙතන ඉඳන් තමයි අපි මේ pavement එක rotate කරන්න පටන් ගන්න. හරි, rotate කරන් ඇවිල්ලා හරියට මෙන්න මේ point එකට එනකොට මේක full super elevation එකට ඇවිල්ලා තියෙන්න ඕන. හරි, අන්න එහෙම තමයි අපි super elevation එකක් position කරගන්න. Right, so we have to keep 2/3 of LE prior to the tangent point and 1/3 of LE within the curve. හරි නේද? Right. Right. This is the full figure, right? Full figure. This is the straight section, right? And this is the super elevation development length. This is the tangent point, right? So this is the level point. So you can start turning the payment from this point, and we have to come to the full super elevation at this point. So this length we called as the super elevation development length, right? So this is the figure that we have drawn earlier, right? Ah, then draw this one. So this is the very important one, right? This one, right? So here the normal crown section start rotating this point, then this will come to the flat position, again rotate, it will come to the straight like this, then again we rotate these two, right? Then it will come to the full super elevation, right? Quickly draw this one. Right. Next. Right, we have exercise, right? Find the super elevation development length using the data given below. So road type is two-lane two-way road. Lane width is 3.5 meters. Shoulder width is 0.5 meters. Normal cross pole minus 2.5. Design speed 80. Radius of the curve 280 meters. Rate of pavement rotation 0.025. So what you have to do is you have to do the so you have to calculate the super elevation development length for the from the both methods. Right, then we go with the highest value. Right, so first you can write down this question. Right, then we'll have a discussion. Right, first write down this question. Otherwise, you need the data. Right. So if you have written down, you can start the answering the question. So I will move to the previous slide to get this. But we need the GR value, right? So we need the GR value. The design is speed 80, and this is two lane two way. Two lane two way. We need GR value. GR value two lane two way. Speed is 80, 0.75. Right. You can have GR is so uh, 80. This is two lane two way means we are rotating only one payment, right? So you have to keep it in mind, right? So if this is a two-way two lane road means we have two lanes, but we have two lanes, but these two lanes are in two different directions. This is in this direction and this is in this direction. So when we are rotating the pavement, we are rotating only one lane. Therefore, you have to use the one lane and speed is 80. So our GR value is 0.5. Right? So you have to keep it in mind. So if this is a two-way road, only one lane is rotating. Therefore, we have to take GR as 0.5. So in this case, GR is 0.5. Right. Now you can take 3 minutes and you can start the calculation. Yeah. You can start. So this is 0.5%, right? So now you can start the calculation. I will give you 3 minutes. Right, shall we discuss? Right, so width is given as 4 meters, right, 3.5 lane and 0.5 shoulder. Then normal crossfold is minus 2.5. Then V is 80, R is 280, beta is 0.025. So first we have to calculate the super elevation, right? E plus F is equal to V squared over 127 R. For 80 kilometers per hour, F is equal to 0.14, right? The friction. Then E plus 0.14 is equal to 80 squared divided by 127 into 280. Then you can calculate the super elevation, that is 0.04. Right? First we need the super elevation. Then we can go for relative gradient method. So from the relative gradient method, the LE is equal to W times E plus N divided by GR. Right? So here only one plane is rotating. Therefore, as I explained, this GR value is 0.5. Then you can directly calculate LE, that is 4 into 4 plus 2.5 divided by 0.5. Then the super elevation development length will be 52 meters. Then we go for the rate of payment rotation method. So from the rate of payment rotation method, LE is equal to E plus N times V divided by 3.6 beta. Right? E is, so as I explained previously, here in this relative gradient method, this is a percentage and GR also percentage. Therefore, the percentage will cancel out. For that one, we have to substitute in percentages. Here is 4%, so you have to apply 4 here. N is 2.5%, you have to add 2.5 here, right? And also this is minus 2.5, right? But here it is plus. So what is the reason? Now we are rotating this payment from the normal count section. We are rotating this one from the normal cost pole. So this is 2.5, and we rotate this one up to 4. Then altogether this is 4 plus 2.5. මෙන්න මෙතෙන්ට දාන්න ඕන මේ payment එක rotate වෙන total amount එක. කොච්චරක් මේක rotate වෙනවද කියලා. එතකොට මේක -2.5 ඉඳලා 4 නැතකොට 4 දාලා -2.5 දැම්මොත් එහෙම 1.5 නේ එන්නේ. එහෙම නෙවෙයි දාන්න ඕන. හරි ඔක -2.5 වල ඉඳලා මෙහෙම තියලා ඔය 2.5 කරගලා 0 වෙලා තව 4ක් අනිත් පැත්තට කරගෙන. ඒක තමයි උතන වෙන්නේ. හරි එතකොට මේ දෙක ඇඩ් කරලා තමයි ඔන්න දෙන්න දාන්න ඕන. 4 plus 2.5. Right, then L is 52 meters. Then in the rate of payment rotation method, right, we are applying beta value, so we have to substitute E and N in terms of decimals. Now decimals වලින් දාන්න ඕනේ මේක. E is 0.04, N is 2.5 means 0.025. V is 80, 3.6 into beta, 0.025. Right, then for that case, the super elevation development length is 57.78. The මේකෙන්නේ appearance එක. appearance එකට කියන අපිට පාර යනකොට අංගු දැක්කහම හොඳ appearance එකක් තිබ්බොත් තමයි driverට confidence පිට ඒක ගන්න හිතෙන්නේ. නැත්නම් යා කොහොමද slow කරනවා අපි කොච්චර speed දියද කියලා. හරි අන්න ඒකට අපි තියන්න ඕන super elevation development length එක 52 meters. හැබැයි ඊළඟ එකෙන් එනවා comfort එකට 57 meters ඕන. එතකොට ওই දෙකම satisfy වෙන්න we have to go with the maximum value. So we are selecting the maximum value from 52 and 57.78. Then the super elevation development length is 57.78 meters. මේක තමයි අන්තිමේට එන්නේ. Right. ලියාගන්නකෝ answer. Right. Next, the pavement widening. Right, pavement widening is something, a small thing, right? So when if we think about long vehicle, so when it takes a horizontal curve, then the rear wheels are not coming in the same path as the front wheel. හරි ඉස්සරහ රෝද ගාන්න පිටිපස්සේ එන්නේ නැහනේ. So we need some extra width, right? So that is called the extra widening. The amount of extra widening required depends on the radius of the curve, width of lane on a straight road, length of vehicle length and width, vehicle clearance. Right, then the minimum widening is 0.6 meters. Right, we have this chart in the design guide. So from this chart we can calculate the amount of extra widening. So here you can see there is a margin here, but as I told here, the minimum value of extra widening is 0.6 meters. You can see that under this margin we have 0.3, 0.4 something like values, right? So those are less than minimum, so we are not using those values. So in that case, for this one, if we are going for a extra widening, we have to at least provide 0.6 meters. So I will share this, right? Right. Right. Then we have to study about the vertical alignment. Right now, the horizontal alignment part is over. Right. Do you have any questions from that one? ඒක තේරිච්ච නැති මොන හරි කියනවද horizontal alignment එක? නැද්ද? ඉන්නවද කොරමද? Right, then we can go for vertical alignment. Right, vertical alignment is the longitudinal profile along the center line of a road. So it is made up of a series of grades and vertical curves. The vertical alignment is typically displayed on a longitudinal section or the longitudinal profile. So I have explained that one previously, right? Then gradients. The grades are generally expressed as a percentage of the vertical component divided by the horizontal component. Gradient කියලා කියන්නේ if this is the road, the gradient means vertical component divided by horizontal component. Y divided by x. පොඩිකාරකරන අනුක්‍රමණය කියන්නේ. The same thing here, and we have to express this as a percentage, 100%. Right, then there are some maximum gradients for a road, so that will depend on the road class and the terrain type. Right, so road class we can divide into 5, A, B, C, D and E, and the terrain type we can divide into 3, flat terrain, rolling terrain and mountainous terrain. F means flat terrain, R means rolling terrain, M means the mountainous terrain, and these are the gradient values. So we have discussed this previously. Right, then there is a minimum gradient also. Right, we are not constructing the roads very stretch because of the drainage problem. Therefore we have to provide at least a small gradient. So the minimum gradient is 0.3% for urban roads and 0.5% for rural roads. හරි අපිට කෙලින් වගේ පාරක් වෙනකොට කෙලින් නැහැ, පොඩි gradient එකක් හරි පාරක තියෙන්න ඕන. Right, then critical length of gradients. Critical length means maximum length. So if we have a section with gradient 3%, so we can continue that 3% gradient up to 480 meters. Then we have to reduce the gradient. හරි gradient එක එක දිගට කිලෝමීටරයක් විතර තියාගෙන යන්න බෑ. කන්දක්නේ gradient එකක් කියන්නේ. ඒතකොට ඒක එක දිගට කිලෝමීටර ලොකු දුරක් අරන් යන්න බෑ. එතකොට ඒක වාහන වලට හොඳත් නෑ. සේෆ්ටි වලට හොඳත් නෑ. ඒක එහෙම තියන්නේ නැහැ. හරි ඔයාලා නිකන් බලන්න නුවරඑළිය පැත්ත යනකොට උනක් බලන්න පාරේ කන්ද එක දිගටම නෑ. ඒක එක දිගට වගේ දැනුණාට පොඩි පොඩි පැත්තෙන් හදලා තියෙන්නේ මේ විදිහට තියෙන්නේ. එක දිගට කන්ද නෑ. හරි පොඩ්ඩක් අඩු කර කර වැඩි කර කර යන්න ඕන. අපි දැන් කන්ද කියලා තේරෙනවා ඒනට පොඩි ප්‍රමාණයක් ෆ්ලැට් වෙලා කියන්නේ මෙහෙම නැගලා ඉන්න පොඩි ප්‍රමාණයක් ෆ්ලැට් වෙලා කියලා තමයි ආයිස් එන්නේ. Right? So if it is 3% gradient, we can go for 480 meters. If it is 4.4% gradient, we can go with 330 meters. So likewise, when the gradient is increasing, the critical length is decreasing. Right. Then when calculating the vertical curves are usually parabolic in shape. Right? Parabolic එකක් වගේ තමයි තියෙන්නේ. So parabolic shape means පොඩි කාලේ අපි හඳින්න පරාවලය කියලා එකක්. Right? Like this. Or it can be like this. Now shape එකෙන් තමයි vertical curves තියෙන්නේ. Right? So they are expressed as by using a k value. The k value is the vertical curve constant. So we call it as the vertical curve constant used to define the size of a parabola. It is the length in meters required for a 1% change of gradient. මේ gradient එක 1% change වෙන්න නම් තියෙන්න ඕන distance එකට තමයි k කියලා කියන්නේ. මේ පස්සේ බලමු. Minimum k value vertical curve should be selected on the basis of three controlling factors. So we have three controlling factors when designing a vertical curve. Right? First one is the side distance. Second one is the appearance. Third one is the riding control. So we have to check the side distance, appearance, and the riding control. Right. So for a simple parabola, the rate of change of gradient per unit length is a constant. But a simple parabola එකට rate of change of grade per unit length කියන එක constant එකක් වෙනවා. So that constant is equal to k. Then k is equal to L divided by A. L is the length of vertical curve. A is the algebraic difference in gradients. And when we gradient දෙකේ වෙනස. As example, if this is 3% gradient and this is minus 2% gradient, minus, right? Then A is equal to the total change is 5. 3 වලින් ඉඳලා ඇවිල්ලා 5 වලට මේ 2 වලට minus 2 වලට කරගෙන ගන්න ඔක්කොම 5. Then A is equal to 5%. මොනකට තමයි අපි A කියලා කියන්නේ. Right? Okay. So this k value is important when calculating the vertical curve length. Right? You can write down the equation and you can sketch the figure also. පොඩ රූපයෙන් දෙගෙන බලා ගන්න මේ ලියා ගන්නකො. Right. Then we have two types of vertical curves: convex vertical curves and concave vertical curves. Right. So these are convex vertical curves like this. Do it like this. So here this top point we called as the summit. Right. In crest vertical curves, the summit is at the top, and in sag vertical curves like this, so there is the bottommost point. Right. So these are crest curves. Oh, and these are sag curves. So we have to do the calculations for both crest curves and sag curves. But before moving on to that one, you can draw these two types also. Right. Then you have to go for the side distance criteria. So yeah. So with the time, I'm not going to continue that one. So I will continue that one in the next day. So do you have any questions up to this point? Miten ka mahargi na dahan. No, right. So if not, we can wind up the session. Right. Yeah. Okay, then I will stop here. So thank you very much for your participation.
Thank you, sir. Good night, sir.
Good night.
Thank you, sir. Good night.
Good night.